For my revision 2 board, one of the main changes I wanted to make was to change the algorithm switch from a 4-way switch to an 8-way switch, and in order to do that, when binary encoded, I needed to change from using 2 GPIO pins to using 3, and I didn't have a spare GPIO pin, so on the revision 1 board I was using a dedicated output pin for the LED, but on the revision 2 board I'm going to drive the LED from the internal clock output from GPIO pin 21, and so that means I can win back an extra pin. So I've jiggled around everything on this side so that it's all nice and neat, and the GPIO pins are physically grouped with each other. So I've got three pins for the algorithm switch, 4 for the divisor, then I've got the I2S interface, and I've had to bump that all up a GPIO pin, but then everything else remains the same. So I've got the rotary encoder with its switch, the soft mute output, and then the SPI bus signals, my sync free switch, and external clock in, external clock out, and the analog to digital converter ports for the 3 potentiometers. So I'm going to work on circuitry required to implement these changes. This is the clock output circuit from the revision 1 board, and all I was doing was taking the clock out from the Pico and using a small signal transistor, NPN transistor, to switch it between the 12 volt and 0 volt rails. So as the clock output goes high, the transistor conducts and the clock output here goes low. So the ultimate clock output is phase inverted compared to the pin from the Pico. And separately, totally separately, I was using another pin to drive the LED, and when this pin goes high, the LED comes on. So in order for the LED to come on when the clock output goes high, I needed to invert the phase between these 2 pins, which I was doing in software. So far so good. However, I want to win back this pin. Now I can't just connect the LED to the existing clock output, because then the LED would be the inverse of the ultimate clock output signal. So what I need to do is put an extra inverting stage on the output here. So what I've come up with is this, to add another inverting stage to the clock output using a PNP transistor. So that means I can connect my LED directly to the Pico's clock output port, and using a second inverter, that means the ultimate clock output from the module maintains the same phase, and the LED will come on when this ultimate clock output goes high. But I need to test that. Software wise, I've got an extremely simple little program that just polls a pin and sets the clock output pin accordingly, so I can feed a signal in and I'll get the same signal out. But at least that lets me test the Pico 2's GPIO pin output. I've mocked that circuit up on some breadboard, so here I've got exactly the same clock input circuit that I used on the revision 1 board with a little NPN transistor, and here I'm connecting the output LED directly to the clock output pin on the Pico, and this jumble of resistors and NPN and PNP transistors form the kind of double inverted output buffer for the clock output signal, and I'm feeding in a very slow square wave, and as I showed, just polling that and setting the output pin accordingly, and I can see that my output is switching between a pretty good 0 volts and a pretty good 12 volts. So yep, that seems to work perfectly. As a bit of a further test, I'm feeding in an audio rate signal. This is a 400 Hertz square wave that I'm feeding in, and yeah, the output's switching quite nicely, quite quickly, so yeah, pleased with that. Other changes to the circuitry: instead of the LM1117 5-volt regulator, which has the tab on the 5-volt output, I'm going to use a 7805 in a D-squared pack configuration, which has the large tab on the ground, pin 2. So that means I can put it on a larger copper area to dissipate some more heat. In order to try and improve the thermal conductivity for the 7805 5-volt regulator, which is in a D-squared package, a TO252, I've taken the footprint for the TO252 and I've extended the ground pad, pin 2, beneath it, so that it looks like this. And I've added a second pad on the back copper layer, and then I've added a lot of plated through vias between the two layers. So now if I look at the 3D viewer, it looks a bit like this. We've got an area of front copper and back copper which is not solder masked, and we've got a number of, you can just see them in there, a number of vias connecting the two sides together, and my hope is that this will improve the thermal conductivity between the two layers and help to cool down the 5-volt regulator. I'm replacing the 4-way algorithm switch with an 8-way, and that means I'll need to use a second MC14532 8-bit priority encoder, and it will add to the resistor count, but shouldn't be a problem. Finally, I'm changing both the multiply divide switch and the sync free switch to use internal pull-up resistors, and for the switch to switch the inputs to ground, and this neatly overcomes the so-called GPIO bug in the Pico 2. Layout wise on the PCB, most of the components in the same positions. I've moved these connectors in by 1mm because the auto router was trying to route a lot of tracks up the outside, and it was getting a bit close to the edge of the copper pore. I've rotated both of the multi-way switches. Well, obviously I've changed one to an 8-way switch from a 4-way switch, this one here, and I've rotated them by 90 degrees. I've also rotated the input volume control by 180 degrees, and because of its physical pad or footprint layout, I've had to move it up the board by 1mm. So I've moved the input and output clock sockets up by 1mm. I think the final change is I've moved this LED closer to the clock output port, and obviously I'm now using a D-squared pack 7805 regulator for the 5-volt regulator, as opposed to the LM1117 that I was using before, and some of the associated components have therefore changed. So now time to run the auto router around this. Once again, I've let the auto router do its thing, and as before, there's a couple of errors that it highlights where it can't connect various nets together across my keep out zone across the middle, but I know that these are connected by virtue of the plugs that are back to back. And so if I now look at my board in 3D, you can see my DPAC package with the large keep out zone, and everything else, yeah, looks pretty good. All my switches rotated, and yeah, I think I'm pretty much ready to send this off for manufacture. Generating the Gerber files and drill files really is as simple as clicking on File, Fabrication Outputs, Gerbers, making sure that we've included all of the important layers that have information on, including the user Eco1 layer, which is my V-score that I forgot last time. Plot that. There we go, done. And generate drill files. Keep the defaults. Done. Add all of those into a zip file. There we go. Open the PCB Fabricators website. This is PCB Way. Other fabricators are available. Quick order PCB. Add Gerber file. Add the zip that we just created, and that gives me an instant quote of 56 euros, which is about 45 of our English pounds. So I'm going to go ahead and order that.